activity 1, algebraic sensitivity analysis objective. So for this part, use the graphical sensitivity analysis to determine conditions that will maintain the optimality of the input variable at LP. So reduced cost. It is to facilitate the explanation of the objective function sensitivity analysis. First, we need to define the reduced cost. So reduced cost per unit is equals to cost of consumed resources per unit minus revenue per unit. The given definition of reduced cost, we can now see that an unprofitable variable such as XI can be made profitable in two ways. First, by increasing the unit revenue, and second, by decreasing the unit cost of the consumer. So optimality ranges. This figure, to compute the reduced cost for any variable, multiply the elements of each column by the corresponding elements in the leftmost column and add them up and subtract the top row element from the sum. Dual problem. It is an LP defined directly and systematically from the primal LP model. For various forms of primal depending on the sense of optimization type, constraint, and the orientation of the variable. For this reason, we offer a single definition of automatically subsumes all forms of primal. So construction of dual from the primal. So in this figure, first we have a dual variable. It is defined for each primal equation. Also, there is a dual constraint. It is defined for each variable, and the constraint, which is the column coefficients of a primal variable defined the left hand side coefficient of the dual constraint and its objective coefficient defined the right side. And lastly, the objective coefficients of the dual equal to the right side of the primal constraint equation. Next. So for the rules of constructing the dual problem, uh, the sense of optimization in the dual is always opposite to that of the primal. An easy way to remember the constraint type the dual that if the dual objective is minimization, then the constraints are all type greater or equal. The opposite is true when the dual objective is maximization. Next. So the summary for constructing the dual problem. Uh, this slide, in this table, this the summary for constructing. So the table does not use this designation primal and dual. What matters here is the sense of optimization. If the primal is maximization, then the dual is minimization and vice versa. Next. Primal dual relationship. Changes made in the original LP model will change the elements of the current optimal function, which in turn may affect the optimality and or the feasibility of the current solution. These relationships will form base for the economic interpretation of LP model as well as for the post-optimality analysis. So this is the review of simple matrix operation. First, we have the row vector times matrix. Next. Second is the matrix times column vector. Next. And third is the scalar times matrix. So we have here the layout for the simplex W. It gives a schematic representation, the starting and general simplex W. This starting W, the constraint coefficients under the starting variable may from any identity matrix. This arrangement, subsequent iterations of the simplex W generated by Gauss-Jordan row will modify the elements of the identity matrix to produce what is known as the inverse matrix, which is the inverse matrix is the key to computing all the elements of the associated simplex W.
So in optimal dual solution, the primal and dual solution are so closely related to the optimal solution of either problem directly yield the optimal solution of the other. An LP model in the number of variables is considerably smaller than the number of constraints. Computation saying may be realized by solving the dual from which the primal solution is determined automatically. So,
So, ako na.
mm,
For the optimal dual solution, uh, the dual itself, the primal, which means that the dual solution can also be used to yield the optimal primal solution automatically. So for method one, optimal value of dual variable y is equal to optimal primal g coefficient of starting variable xi plus the original objective coefficient of xi. For method two, optimal values of dual variables equals to row vector of our original objective coefficient of optimal primal basic variable times the optimal primal number, which which the element of the row vector must appear in the same order which the basic variables are listed in the basic column in the table. So lastly, for the primal dual objective values, uh, simply the objective value in the maximization problem is lesser than or lesser than or equal to the objective value of the minimization problem, which is for any pair of feasible primal and dual solutions. Now,
so economic interpretation of duality. So the linear programming problem can be viewed as a resource allocation model in which the objective is to maximize revenue, subject to the availability of limited resources. Looking at the problem from the standpoint, the associated dual problem offers interesting economic interpretation of the LP resource allocation model. So this is viewed as a resource allocation model. The primal problem has n economic activities and m resources. The coefficient Cj is the primal represents the revenue per unit of activity j resource I, whose maximum availability is Bi, is consumed at the rate I Aij units per unit activity j. So for any two primal and dual feasibility solution, the values of the objective function when finite must satisfy the following inequality in the equation below. So the equation below, given the primal problem represents the resource allocation model, we can think of Z as the representing revenue of dollars because BI represents the number of units available of resource I's. The equation, therefore, Z is equal W can be expressed as dimensionally as dollar is equal to summation of units of resource I times dollar per unit of resource I. This means that the dual variable yi represents the worth per unit of resource I. So using the same logic, the inequality z is less than w associated with the two feasible primal and dual solution is interpreted as revenue is less than worth of resources. This relationship says that as long as the total revenue from all the activities is less than the worth of the resource, the responding primal and dual solution are not optimal. Optimality, the maximum revenue, is reached only when the resource has been exploited completely, which can happen only when the input or worth of the resources equals the output or the revenue dollars. So the dual constraints can be interpreted using the states of any primal iteration. So objective coefficient of xj is equal to the left side of dual constraint j minus the right hand side of dual constraint j. We use dimensional analysis once again to interpret this equation. The revenue per unit Cj of the activity J in dollar per unit. Hence, for consistency, the quantity equation must also be in dollar per unit. Next, because Cj represents revenue, the quantity equation which appears in the equation with an opposite sign must represent cost. So dollar cost is equal to the summation of Aij yi is equal to the summation of the usage of resource i's per unit of activity times cost per unit of resource I. The conclusion here is that the dual variable yi represents the inputted cost per unit of resource I, and we can think of the quantity of the equation as the inputted cost of all the resource needed to produce one unit of activity j. So additional simplex algorithm. So the algorithm is sometimes referred to as a primal simplex method. This section presents two additional algorithms, the dual simplex and the generalized simplex. Also, all three algorithms, the primal, the dual, and the generalized, are used in the course of post-optimal analysis calculations. So dual simplex algorithm is the crux of all dual simplex method, is a start with a better than optimal and infeasible basic solution. The optimal and feasible conditions are designed to preserve the optimality of the basic solution while moving to the solution iteration toward feasibility. So there are two conditions in dual simplex algorithm. First is dual feasibility. This leaving variable xn is the basic variable having the most negative value. Ties are broken arbitrarily if all the basic variables are non-negative. The algorithm ends. And the second is dual optimality. It states that given that xr is leaving variable, let C be the reduced cost of non-basic variable x and urj as the constant coefficient in the xr row of xr column of the tableau. The entering variable is a non-basic variable with a rj is less than 0 that corresponds to the equation below. So if arj is greater than 0 for all non-basics xj, the problem has no feasible solution. To start with the optimal and infeasible, two requirements must be met. First is the objective function must satisfy the optimality condition of the regular simplex method. The second is that all the constraints must be of the type less than or equal to. The second condition requires converting any greater than or equal to signs to less than and equal to simply by multiplying both sides by the inequality greater and equal to by -1. If the LP includes an equal constraint, the equation can be replaced by two inequalities. Example is x1 plus x2 is equal to 1 is equivalent to x1 plus x2 is less than 1 and x1 plus x2 is less than is greater or equal to 1. So we change the greater than sign to less than, so x1 plus x2 is less than and greater than 1 and negative x1 minus x2 is less than or equal to negative 1. After converting all the constraints to less than and equal to, the starting solution of infeasible if at least one of the right-hand sided of the inequalities is strictly negative. So generalized simplex algorithm. The general simplex combines both the primal and dual simplex method in one algorithm. It deals with the problem that start both non-optimal and infeasible. In this algorithm, successive iteration are associated with basic feasible or infeasible basic solution. So in this LP model, the tableau from which the starting basic solution x3, x4, xs is both non-optimal because x3 has a negative reduced cost. This and infeasible because x4 is equal to negative 8. The first equation has been multiplied by negative 1 to reveal that infeasibility directly in the solution column. We can solve the problem without using any artificial variables or artificial constraint as follows. Remove infeasibility first by applying a version of dual simplex feasibility condition and select x4 as the leaving variable. To determine entering variable, all we need is a non-basic variable whose constraint coefficient in the x4 row is strictly negative. Extraction can be done without regard to optimal because it is non-existent to the point anyway. In the present example, x2 has a negative coefficient in the x4 row onward, is selected as the entering variable. The result is the following tableau. So the solution in the preceding tableau is now feasible but non-optimal, and we can use the primal simplex to determine the optimal solution. So in the post-optimal analysis, it determines the ranges and the different LP parameters that keeps the optimum basic variable unchanged, deals with making changes in the parameters of the model and finding the new optimum solution. These changes requires periodic recalculation and the optimum solution of the new computation are rooted in the use duality and primal dual relationship. So the following table lists cases can be arise to post-optimal analysis needed to obtain the new solution. So assuming one exists in this table. So in terms of changes affecting feasibility, the feasibility of the current optimum solution may be affected only if one of the right-hand side of the constraint is changed to the second of the new constraint is added to the model. So changes in the right-hand side, this change requires recomputing in the right-hand side of the tableau using the formula below. Additional Addition of two constraints. The first one is the new constraint is redundant, meaning this is satisfies the current optimum solution and hence can be dropped from the model altogether. The second is the current solution violates the new constraint, in which case the dual simplex method is used to restore feasibility. So changes effective optimality. Changes in the objective function coefficient. These changes affect only the optimality of the solution. Such changes thus requiring computing the zero coefficient or the reduced cost. Two cases will result to this. The first one is the new zero satisfies the optimality condition. The solution remains unchanged, meaning the optimum objective value may change however. The second is the optimality condition is not satisfied. Apply the primal simplex method to recover optimality. Addition to addition of a new activity. The addition of the new activity in the LP model is equivalent to adding a new variable. Intuitively, the addition of the new activity is desirable only if the profitable, that is, if it improves the optimal value of the objective function. The condition can be checked by computing the reduced cost of a new variable. If the new activity satisfies the optimality condition, then the activity is not profitable. Else, it is advantageous to undertake the new activity. That will be all. Thank you. I'm Joshua Cinco and my partner is.
Agustin Buhian.
If you have any further question and clarification, please comment down below. Thank you and God bless.